all panelists. And that way the panelists will be able to see your comment and question and have those answered. I'm going to turn this portion over to our moderator, Lauren Collins. Thank you so much.
Hello, everyone, and thank you for joining us. Before we get started, just to reiterate, throughout the presentation, if you have any questions, please chat them in and make sure that you are sending them to all panelists. I will be keeping a parking lot of questions, which we will review at the end of the presentation. We will try to get to as many as possible in the order they come in. If any questions are not addressed during the webinar, they will be addressed offline at a later time. So without further ado, I'd like to turn it over to our presenter, Dr. Felix Eldert.
All right. Good morning, good afternoon, everybody. Today is part 2 of our session on using directed acyclic graphs, DAGs, graphical causal models, for advancing tobacco-related research. So what I will, all right. So here are the main readings of papers that I'm going to draw on for this presentation. I will draw on a few additional readings that are cited throughout where appropriate in the slides. Good. So I trust that most of you have attended the first meeting 2 weeks ago where we introduced the basic logic of working with DAGs. But because it's been 2 weeks, I'm going to review briefly the main lessons that we have learned first. After I've done that, which really should only take 5 to 7 minutes, we're going to go through 3, more or less famous examples and pressing examples from tobacco research and show how we could start working with DAGs to sort of get a very immediate and fast understanding of the problems that may either bedevil those applications or that might shine light on famous prior findings. The first example that I will discuss is a proposal for the resolution of the smoking birthweight paradox. This is going to be using work by Tyler Vanderweel, who has analyzed this problem using DAGs as well as others. The second problem that we're going to deal with is whether smoking actually has an effect on birthweight. Research suggests that it does. The question is how can we use potentially instrumental variables in Mendelian randomization to be extra sure that smoking causes low birth weight. And then finally, in a much more exploratory kind of hot topic issue, we're going to talk about the question of whether flavored tobacco products or vaping could be understood as gateway products. And here I will offer some design considerations to highlight known, or perhaps well-known or perhaps less known problems in this type of research, which is a very active area of research right now. Good. So much for the overview. Now let's go into our review of work. Oh, sorry, I should have said, of course, in the end we'll have time for questions. So last time we have met DAGs. DAGs are graphical causal models. They look like this, and we learned to interpret them as non-parametric structural equation models. That's very technical language, but really that just means that the DAG is a graphical representation of the qualitative causal relationships between variables in the data generating process. So the DAG consists of variables, it consists of direct causal effects, and it consists of absent causal effects. That is, there are some arrows missing in this DAG. We reviewed that these missing arrows are really important because they represent exclusion restrictions that help us justify any identification analysis. So we will meet a lot of missing arrows today in order to talk about solutions for identification problems. Now, there are four main uses for graphical causal models in the biomedical and social sciences. First, of course, people are using graphs as an efficient notation for the qualitative causal assumptions that the analyst is making about the data generating process. The DAG is a picture of the world, if you will. It describes the beliefs, assumptions, knowledge about the world that we commit to, and that we have to commit to in order to justify any sort of causal inference from any sort of data. So that's great, right? Causal inference requires causal assumptions, and the DAG is an efficient means to notate the qualitative causal assumptions that applied scientists are comfortable talking about. So then, once we've notated the assumptions, we come to the second use of DAGs, which is to link the causal assumptions of the model to the statistical associations that we might observe in data. So the DAG works as a translation tool, really. It translates between the analyst's theoretical subject matter knowledge and the analyst's data mass. So clearly those translation rules are important, and we're going to review them in a second. Third, once we've understood which associations in the world could be originating from the causal model, if our assumed causal model is true, then we have everything we need to support causal identification analysis. That is, assuming that our assumptions about the world are true, we can ask which associations in the data represent the desired causal effects and which ones are not causal effects. Good. And once we've done that, it's just a really small step to informing all sorts of problems and solutions in statistical estimation and in the design of research, which we will talk about today. Now, here's some terminology that we need to review. First, you remember that all associations in DAGs flow along paths. And paths are really any non-self-intersecting route between two variables. Now, importantly, we distinguish between causal paths and non-causal paths. Causal path from a treatment to an outcome is a path that points strictly away from the treatment and strictly toward the outcome. So in this DAG here, if T is the treatment and Y is the outcome, then we only have one causal path, namely T to Y. A non-causal path between a treatment and an outcome is any path where you travel against the direction of the arrows at least once. So here we have two non-causal paths between T and Y, T-U-Y and T-X-Y. These non-causal paths are important because they represent potential sources of spurious association. In other words, the non-causal paths are the sources of bias in our analysis. And then finally, we met a type of variable called a collider variable, such as T. And a collider variable is a variable into which two arrows point along the path. So let's look at T. The variable T is a collider on the path from X to U to Y, because on that path from X to T to U, two arrows point into T. That makes T a collider. Now, all right. So this is the last review slide. You remember that the analyst needs to know how causation relates to association in order to infer causal effects from our observed data. The only thing we can observe in data are associations, so covariances, correlations, regression coefficients. Those are all measures of association. And we want to know under what conditions our, say, regression coefficients or other measures of association have a causal interpretation. So here's the process, just in brief. The first step is to note that the causal effects in the data generating process, so the causal effects that you've notated in the DAG, give rise to observable associations in the data. Now, how do they give rise to it? Well, they give rise to them by making association flow along paths. Now, it turns out that only open paths transmit association, whereas closed paths do not. Hence, we ask, which paths are open, which ones are closed? And the answer to that question is given to us by the D-separation criterion. The D-separation criterion, which we introduced last time, determines whether a path is open or closed. Now, the D-separation criterion itself can be kind of unwieldy, but particularly if you're new to using DAGs, it's important to remember that the D-separation criterion is just a fancy way of putting together three basic rules of association. Because it turns out that all associations between two variables originate from three causal three causal structures. First, two variables A and B will be associated if A directly or indirectly causes B. So that's causation, association by causation. Second, two variables A and B will be associated if they're caused by a common cause, C. So that's the structure of association by confounding. And third, and that's the hard one, two variables A and B will be associated if we condition on a common effect, C, or a descendant of a common effect, D. This is the structure of endogenous selection bias. So again, the point here was that two variables A and the association between A and B will change if we condition on a collider between them, or on the descendant of a collider between them. Good. So then finally we've said that we can identify the causal effect of the treatment on the outcome if we can isolate the association that flows just along the causal paths while closing all the non-causal paths between treatment and outcome. So that's the goal here. We want to condition on a bunch of variables to close all the non-causal paths and leave all the causal paths open. We're done with review now. Okay. So now let's see if we can use these basic rules of working with directed acyclic graphs in order to shed some light on some important tobacco research-related problems. So the first example that I want to discuss is Tyler Vanderweel's analysis of the Birthweight paradox. The following slides are closely based on Tyler Vanderweel's paper. So, okay, so here's the setup, as of course you are well aware. Yerushalmi, about 40 years ago, described what's now known as the Birthweight paradox, which really describes a set of rather counterintuitive findings. First, it's well known, indubitably documented with empirical research, that maternal smoking during pregnancy is associated with both low birth weight and increased neonatal mortality in the aggregate. So there is this association, there is no doubt. But, and this is the counterintuitive part, among low birth weight babies, maternal smoking is associated with decreased neonatal mortality. And this is an apparent paradox because it contradicts intuition. Specifically, against the strong scientific prior that smoking is thought to be harmful to all babies, what's at stake in this paradox is the interpretation of the second finding. So the question is smoking in fact beneficial to low birth weight babies, or is this association perhaps the result of a methodological artifact? So a number of scholars have suggested solutions to this problem. I will review here the one that has gotten a lot of play in recent literature and has assumed an important place in working with DAGs in this type of research. So here's one explanation. One explanation is that perhaps this positive association between maternal smoking and infant survival among low birth weight babies is an artifact that's owed to selection bias by stratifying an intermediate variable. So let's first look at this DAG here and see what it means, and then we're going to analyze it. Okay. So this DAG consists of 4 variables. S is maternal smoking. And suppose, for argument's sake, that we have randomized maternal smoking. I know we can't, but let's just assume that to highlight the essential structure of the problem. So we have a randomized experiment where we give pregnant women either a bunch of smokes or we don't. Then L is whether the woman gives birth to a low or normal birth weight baby. And Y is an indicator of neonatal mortality. Now, the key problem that we're going to face is that even if smoking is randomized, low birth weight is not randomized. So surely, low birth weight is going to share causal risk factors with neonatal mortality. For example, this common risk factor of L and Y, U, could represent malnutrition, birth defects. So the story here would be that if U is malnutrition, well, certainly malnutrition will affect low birth weight, but malnutrition will also affect neonatal mortality. Same for birth defects. Okay. So the point here is that even in a randomized experiment where we have no confounders of our treatment S, intermediate variables are usually not randomized and may in fact be confounded by unobservable. So what does that do? Why is that a problem? Well, recall that the analysis stratifies on L. Actually, there should be a box around the L here because I want to denote that we're stratifying on L, right? We're now restricting the analysis to low birth weight infants. So we've stratified or controlled or conditioned on L. And what does that do? Well, note that L is a collider variable on a non-causal path from S to Y. That path is S to L to U to Y. Does everybody see that? Okay, good. So L is a collider on this path because 2 arrows go into L at this point. Now remember what happens when you condition on a collider. Conditioning on a collider opens the path that goes through the collider and induces an association between the collider's immediate causes. Thus, conditioning on L will now open up a non-causal association between S, U, and Y, such that the conditional association between smoking and birth weight, conditional on low birth weight, is no longer purely a causal association. It has a spurious component. Now, if this path that we've just opened up is negative, then the association between smoking and neonatal mortality, giving low birth weight, could become negative even if the true direct causal effect of S on Y is, in fact, positive. Words, conditioning on L could suggest a negative association between smoking and birth weight, between smoking and neonatal mortality among low birth weight babies, even if the true direct causal effect of smoking on neonatal mortality is positive. Sensitivity analyses that have been done in prior work in our cited in Vanderweel's paper do suggest that it doesn't take much to make this story plausible with actual parameter values. Okay, now let's move on. So far I've just given you a mechanistic explanation. I've given you the mechanistic explanation that says, hey, if you condition on the collider, then that'll open up a path. This path from S to L to U to Y is non-causal, and hence you now have a non-causal association in your estimate. Good. So that's mechanical, and that's perfectly fine. That's a valid explanation, but it doesn't give us intuition. So let's now add some substantive intuition to make this finding clearer. The substantive intuition is the following. Suppose that U is malnutrition, okay? Now, if it's the case that maternal smoking and malnutrition both cause low birth weight, as we claim in this DAG, then low birth weight infants whose mother did not smoke are likely malnourished, or vice versa. Again, if I have a low birth weight baby and the mother did not smoke, well, then that probably means that the infant was malnourished. And if I have a low birth weight baby whose mother was not malnourished, well, then she's likely been a smoker, because something needs to have caused the low birth weight. In other words, conditioning on L gives us a negative association between smoking and malnourishment. Good. All right, now, second step is, if malnutrition is worse for mortality than maternal smoking, and under this story, low birth weight infants of non-smoking mothers may actually have higher mortality. Again, if malnutrition is worse for neonatal mortality than smoking, as is plausible, then low birth weight infants of non-smoking mothers likely have higher mortality. So there you go. You both have a mechanistic story, which we've done on the previous slide, and now a substantive story that accounts for the possibility that the birth weight paradox is due to conditioning on an intermediate variable. Now, the larger lesson here is that conditioning on an intermediate variable is generally a bad idea if we're trying to estimate a total causal effect. So if we want to know, is smoking bad for neonatal mortality, we probably should not have conditioned for that intermediate variable, because doing so almost certainly induces bias of the type that we have analyzed here. And this type of bias is what we call endogenous selection bias, inasmuch as intermediate variables are likely colliders on non-causal paths. Good. But perhaps you're not interested in the total causal effect of smoking on neonatal mortality. Perhaps you're interested in the direct causal effect of smoking on neonatal mortality, that is, among low birth weight babies, which would be represented by this direct arrow here. Or you might be interested in the indirect effect of smoking on a neonatal mortality that's represented by the straight line that goes through low birth rate. Right? You might want to know, to what extent is the overall effect of smoking on low birth weight mediated by smoking causing low birth rate? Well, so we need to do something about this open path, right? So the solution here would be to condition on U. If we have measures of a malnutrition and birth defects, if we have measures on all of the common causes between low birth weight and neonatal mortality, then we could condition on U. Now you'll note that in contrast to L, U is a non-collider. And we recall that conditioning on a non-collider blocks the path. So even if you control for L, if you stratify on L, if you additionally control for U, then you're blocking this non-causal path again. Thus, you could run an analysis where you look for the effect of smoking on neonatal mortality among low birth weight babies if you also condition for U. Good. And using new tools for causal mediation analysis, we could actually also quantify the indirect effect of smoking on neonatal mortality that goes via low birth weight. And research shows that actually, to the extent that we're able to identify the causal effect of smoking on birth weight, most of that effect is mediated by low birth weight. Good. Okay. That's the birth weight paradox. Let me move on to the second example that I want to discuss. So now let's ask, does maternal smoking actually cause a change in birth weight? Right? So this was taken as a valid premise in the birth weight paradox. And now we're trying to be super conflicted, and we're saying, is this really true? All right. So fact. And I should say that here I'm following arguments proffered by Wiebe and colleagues in 2011, so I've just cast this into DAGs and highlighted certain aspects of the analysis. So as we all know, it's a fact that ordinarily squares regression or just simple correlations show a negative association between maternal smoking and infant birth weight. Smoking mothers have smaller babies than non-smoking mothers. The question we want to ask now is whether this effect is causal. The secondary question we want to ask is, can we show this easily with a DAG? Okay, now the problem that we're facing is unobserved confounding. So let's look at the structure of this DAG. Here we have S, that's smoking, L is low birth weight, X are observed common causes of smoking and low birth weight, perhaps a measure of mother's socioeconomic status. But there might also be unobserved shared risk factors between maternal smoking during pregnancy and low birth weight. Those unobserved factors might include the mother's propensity for risk-taking. So for example, it might be that there are women who take a devil-may-care attitude towards their pregnancy in general, so hence they might be more likely to smoke, but they might also be more likely to drink and ride monster trucks down rocky slopes, which might affect the health of the infant and hence cause low birth weight. Okay, so certainly there are unobserved risk factors between S and L. Now, why is this a problem? This is a problem because if we're running an ordinary regression model, we can only control for variables that we actually observe. Now, let's see what now we're going to use the rules that we've learned to see the components of the overall association between smoking and low birth weight. The overall association is a composite of three things. First, smoking and low birth weight may be associated because smoking causes low birth weight. Second, they may be associated because of observed risk factors, confounding, and they may be associated through this open path that goes through U factors. Now, in a regression model where you control for X, controlling for X would block the non-causal path from smoking to low birth weight because X is a non-collider. Non-colliders, conditioning on non-colliders blocks a path. But we can do nothing in regression about the U. The problem is that S to U to L is a non-causal path that is open, and the only way to block it would be to control for U. Don't observe U. So we have a problem. Hence, after controlling for observed confounders, the association between smoking and low birth weight may only partially be causal, and additionally be partially spurious due to this open path from S to U to L. So what are we to do? Well, one strategy could be to theorize the content of U. So once we know that unobserved risk factors are a problem, we could try to figure out what those unobserved risk factors are, apply for a beautiful grant, and actually collect data on U. But suppose you can't do that. Perhaps you're not sure what U is, and if we don't know what U is, then we can't very well collect data on it, much less condition on it. So one proposal would be to solve this unobserved confounding issue for the use of an instrumental variable. In the past, people have used prices as an instrument, and here I'm going to review the Weeby study, which proposes using genes as instruments in a form of Mendelian randomization analysis. So now let's look at what's happened to the DAG. The DAG's just changed. I've added a variable Z. Let Z stand for genes that are, for some reason, plausible, so are plausibly or knowingly associated with smoking. And here this DAG actually makes a really strong statement. The DAG says that we think that these genes cause smoking. Okay, fine. They only actually need to be associated, but for argument's sake, suppose that these genes cause smoking. So, two things need to be true. First, suppose that we have some genes, some candidate genes, some SNPs, that first are associated with smoking, and second, are associated with infant birth weight only via the causal effect of smoking on low birth weight. Is this true here? Are these two conditions met? Yes, you can use the rules that you've already learned to verify these two conditions. First, are the genes associated with infant birth weight? Excuse me, are they associated with smoking? Yeah, absolutely, because according to our theory here, Z causes S. And if genes cause smoking, then genes and smoking are going to be associated. So the first condition is likely met. The second condition was that the genes are associated with infant birth weight only via the causal effect of smoking on birth weight. So let's see. So this statement, the second statement here, is saying that the only open path between Z and L must be an open path that traverses the S to L arrow. Right? So condition 2 says that any association between infant birth weight and between genes and infant birth weight must go through the arrow from S to L. Let's see. There turn out to be 3 paths between Z and L. The first path is the causal path from Z to L. Z to S to L. And that path is indeed open. So yep, it's true that the genes are associated, under this theory, with birth weight via the causal effect of smoking on the birth weight. But there are 2 other paths. There's the path from Z to S to U to L, and the path from Z to S to X to L. Well, the question you want to ask yourself is whether these paths are open. And the answer is no, they're not open, because on both of these paths, from Z via U to L, and Z via X to L, the path goes through S, and S is a collider on those paths. So as long as you don't condition for S, these 2 paths via U and X will remain closed. So there you go. Under this assumption, genes Z meet the 2 instrumental variables from assumptions. So far, so good. Now, further suppose that the effects are linear and homogeneous. Okay, so you don't really need to make that assumption, but it makes it easier. So suppose that that's the case. If that's the case, then we can use these candidate genes as an instrumental variable that can identify the causal effect of S on L, of smoking and on low birth weight. And the idea of this is that we can identify two causal effects here. We can identify the causal effect of the genes on low birth weight, right? That's just the path alpha times beta in this DAG. And we can identify the causal effect of genes on smoking, which happens to be just beta, just alpha. So then you have these two estimates. The effect of Z on L is alpha times beta, and the effect of Z on S, that's alpha. You divide one over the other, and you have an estimate for beta, your desired effect of smoking on low birth weight. And this operation is going to work even if you have unobserved confounders U. So what's the intuition here? The intuition is that under this model, these genes are kind of random. So you have some randomly induced variation in your treatment smoking, and you're going to use only the variation in smoking that's been randomly induced by Z in order to estimate the effect of S on L. That's why we call instrumental variables analysis a quasi-experimental technique. We are not able to randomize smoking, but we are using randomization that happens in nature, namely the presence of certain genes that may affect the likelihood of smoking. Good, so that's it. That's justification. Now, the next question that you need to ask here as you're working with DAGs is the DAG actually plausible? You'll remember that causal inferences from data are only as credible as the causal assumptions that you've put in. And our DAG here makes some really strong assumptions about the structure of the data generating process. And perhaps you don't believe these assumptions. If you don't believe these assumptions, you might not believe the analysis. So let's see. It turns out that Werby and colleagues have provided a careful discussion for how different data-generating models may imperil their analysis. So I want to review their arguments with graphs. So first, IV estimation will break down if the candidate instrument genes exert an effect on low birth weight that is not mediated by maternal smoking. This is known as the problem of pleiotropy. Yeah, perhaps the genes affect smoking, but they might also affect all sorts of other things which could lead to low birth weight. If that were the case, then we would have what's known as an exclusion violation, a violation of the assumption that Z affects L exclusively via S. So you could do some algebra and show that if you had this new arrow from Z to L, called gamma, then the instrumental variables estimator would evaluate to, well, alpha times beta plus gamma over alpha, which most assuredly does not equal desired causal effect beta. So with this formula, we can even see if the bias is going to be large or small. And it turns out that the bias is going to be large if the direct effect of Z on L is large, because we would blow up the numerator of the term. But it would also be large if the effect of Z on S alpha is really small, because a small denominator also blows up this ratio. So how do Wiebe and others deal with this problem? They deal with the problem by saying that they've searched the literature and they haven't found any known pleiotropic effect of smoking genes on birth weight via any other mechanism but low birth weight. So, of course, this is not proof that the arrow from S to L is not there, This is what we would call identification of, I'm going to use a really harsh term, and I don't mean to be overly critical, but we do call it identification via ignorance, right? We're saying we believe that the arrow from Z to L is not present because we have no positive evidence that it exists. Well, of course, for science, that's a good way to go about it, but we might have to revise our judgment here if new research suggests that the smoking candidate genes may affect neonatal mortality via mechanisms other than low birth weight. Good. But so far, there's no evidence for that. Now, there's another way that this strategy could break down. The IV estimation would also fail if the IV candidate genes are correlated with some other genes that affect low birth weight. Okay, so it could be that our candidate gene Z1 is associated with some other genes Z2 that we don't control for, and hence we would now have a non-causal association between Z1 and L that goes through an open path, a mechanism, other than S. This is known as a violation of instrument ignorability, and again, the IV estimator would evaluate to something that does not equal the desired causal effect of S on L beta. Now, how do we deal with this? Again, we need to resort to theory and prior knowledge and ask whether our candidate gene Z1 may be plausibly associated with some other genes or other factors that might themselves cause low birth weight. And so the key candidate here would be problems of a linkage disequilibrium between our candidate gene Z1 and some other genes that we have not considered. And here again, using a review of the literature, Wiebe and colleagues argue that there is currently no positive evidence for such correlation to exist. Okay, good. So if that's the case, then we don't have to worry about this relationship, and we're back to our original scenario where we can use the smoke candidate genes as an instrumental variable for the effect of smoking on low birth weight. So the overall lesson that I wanted to draw in this example is that we can use DAGs to think about the problem of observational identification with OLS regression. We can also use DAGs to develop some intuition and probe the substantive plausibility of quasi-experimental techniques such as instrumental variables analysis. Using DAGs for IV is fairly exhaustively treated in Judea Pearl's book, Causality, published in 2009. Okay. And now, I want to go through our last example. That's much more exploratory in nature because, this is not a settled issue. Oh, I should have said that, this Wiebe study also finds that smoking reduces birth weight. In fact, they find a really small effect, like other instrumental variables analyses before them have. Okay, so yeah, we still believe that smoking causes low birth weight. Now, let's talk about gateway tobacco products. So this is a hot question right now, as I'm sure you're aware. The question is, are flavored tobacco products and e-cigarettes gateway drugs that initiate youth into smoking and that increase adult tobacco smoking rates? If so, what are the causal elements in this process? Now, there's a growing amount of empirical evidence, mostly descriptive, that has raised the specter that these flavored, or like that the tobacco products that are not conventional cigarettes may play a role as gateway drugs. So some stylized facts are that the majority of current tobacco users got started with a flavored tobacco product. So over 50% of current smokers, young current smokers, got started with flavored products. Another piece of evidence is that menthol cigarettes are especially popular among the young, and their relative use compared to, old-fashioned conventional cigarettes is increasing. but there's also been critical literature reviews in the literature that argue that the structure of this gateway hypothesis is as yet under-theorized. Well, that's a nice thing, because we can use DAGs to sort of think about causal structures. So let's do that. So the gateway question has both descriptive and causal elements. I've given you some descriptive findings already. I'm not going to address those. Here I want to focus on some causal questions. I think, researchers in this field think that there are at least two important causal questions about the use of flavored products for tobacco initiation. So the difference between these questions is whether we want the treatment to be the type of product first consumed, or if we want the treatment to be the availability of certain products. The first question would be, what's the causal effect of first consuming flavored tobacco products versus conventional cigarettes versus no tobacco consumption at age 14 on the number of cigarettes smoked at age 20? So here the treatment takes three values. At age 14, either consume a flavored tobacco product, or consume a conventional cigarette, or do nothing. Then we want to know what these. We want to know the effect of a choice between these three options on the number of cigarettes smoked at age 20. So that's the consumption question. So the availability question is really quite different. The availability question asks, what's the causal effect of the availability of flavored tobacco products at age 14 on the number of cigarettes smoked at age 20? So here the treatment is not what the person actually does. Rather the question is whether having any flavored product available at all makes a difference. I would, doing violence to the subtlety of this area of research, we might say that the first question is sort of a more biomedical question, whereas the second question is more of a regulatory question for tobacco use. So now suppose that we live in a beautiful world where the PATH study has been going on for years. So now we have a population of 14-year-old potential first-time users of tobacco products who are followed longitudinally for 6 years until they've reached age 20. So now let's look at some data. Well, the first piece of good news is that the structure of these two questions is the same. We have a treatment, which may be, in the first type of question, the consumption of flavored versus regular cigarettes versus no consumption at all. And the second question would be, T would mean that flavored products are available versus not. The outcome is the number of cigarettes smoked at age 20. And then in either case, yeah, we probably have some unobserved, we have some confounders that affect both treatment and the number of cigarettes smoked at age 20. And in both cases, that confounder may be the social acceptability of smoking in general in that community. So for the first scenario, social acceptability of smoking cigarettes might differentially push youth into smoking normal cigarettes or flavored cigarettes versus not smoking at all. And in as much as they stay in the same community or are socialized in that community, it will of course also affect how much they smoke at age 20. Now for the availability question, the social acceptability might also affect availability. So in communities that are strong anti-smoking, state legislature may do more to keep specifically a flavored product out of the hand of minors. And those states are likely the same states that make tobacco products in general less accessible to people, and hence you might have reduced smoking rates at age 20. So that's the first point. The causal structure of these two very, very different substantive questions is actually the same. So by analyzing that structure, we can understand common problems. So the first obvious problem is that these confounders of treatment and the outcome might be unobserved. If they're unobserved, then we have an open non-causal path from treatment to the confounder A to the outcome. And since A is a non-collider on that path, we cannot block that path without conditioning for A. So if you don't observe A, any type of regression analysis will fail. So, but something else might go wrong. We might have truncation bias, so I want to give you the structure of that. So suppose that we actually measure the confounders of treatment and outcome A perfectly. Okay, we have this amazing study that takes care of all sort of community-level confounding and family-level and individual-level confounding. It's perfect. So you can condition for A and hence get rid of the non-causal path from T to the number of cigarettes C. But now an analyst might get the idea that we're really only interested in the effect of flavored products on the extent of smoking at age 20 among young adults who smoke. This would give us selection or truncation bias. So the idea here would be that we're truncate, typo here, not the same, but the sample. We should truncate the sample to include only active smokers. This is sometimes done. Correct this. Okay. So what would happen? Well, what would happen is that we're creating truncation bias. Note that the outcome is always a collider between the treatment and all other idiosyncratic causes of the outcome, which we call the error term. Further, recall that conditioning on a descendant of a collider is qualitatively the same as conditioning on the collider itself, in that S is a descendant of the collider C. So conditioning on S will induce an association between treatment and the error term on the outcome. Now, this association will now amount to the creation of a new path, such that conditional on sample truncation, we now have a new non-causal path from treatment via the error term to the outcome, such that the association between the use of flavored tobacco products and smoking at age 20 will not have causal interpretation if we only look among active smokers at age 20. Structure of truncation bias. Okay, but suppose we're with it enough not to truncate our sample in this inadmissible manner. Well, then you might say, perhaps I don't fully observe my confounders, and hence I can't block this backdoor path. Can I find an instrumental variable for my treatment? So let's see. One instrumental variable that's kind of popular in tobacco research is the price, or rather the price differential between different smoking choices. So we might live in a world, the real world, where not smoking is really cheap. Smoking flavored tobacco products or e-cigarettes is, is relatively affordable, and smoking conventional cigarettes is the most expensive of all. So therefore, the price of these different tobacco products might induce variation in what initiation product the youth chooses at age 14. Now, for P to be a valid instrument for T, we've already seen that it must be true that first, price is associated with choice of tobacco product, and second, it must be true that price is associated with smoking at age, with the number of cigarettes smoked at age 20, only via paths that lead through the causal effect from product choice to smoking at age 20. Now, the first condition is likely true. We know that the more expensive smoking gets, the less people consume. Even addicts are rational. This, by the way, is true even in the heroin market. I should say there's good evidence to suggest that even heroin users are price rational. But what about the second assumption? Well, the second assumption is likely false, actually. Inasmuch as pricing depends on what community we live in, because in certain states cigarette taxes are higher than others, and price differentials between tobacco products also differ across states. And inasmuch states or communities differ in the local social acceptability of smoking, then what market we're in will affect both the price and smoking at age 20. So that's a violation of ignorability that we could get rid of by conditioning on M. Secondly, though, if prices are reasonably sticky and people stay in their community, then then prices and price differentials between tobacco products at age 14 may also affect smoking at age 20, because if smoking was cheap at age 14, it's likely still cheap at age 20, and hence prices are not an instrument, but they're a confounder in its own right that needs to be controlled for. Okay, so in summary, we've used DAGs to review the causal structure of some important problems in tobacco research, some solved, some not. What we've done is we've actually used these 40 minutes to go through a large number of structural causal problems that could bedevil our observational data analysis. We've talked about the problem of unobserved confounding, selection on an intermediate variable, truncation bias, and the question of how we find an instrumental variable. With that, I would like to thank you for your attention and participation, and leave some time for questions. Thank you.
Thank you for that wonderful presentation. We're going to move right into questions with the time that we have left. The first question that came in is, in the IV for type of initiation product slide, would price have to be associated with flavored versus big versus none, or just big? In other words, does price have to define T?
Price needs to be, so price needs to differentiate between the product choices. So the choices that we've hypothesized here are the choice of not smoking at all, smoking flavored products versus smoking tobacco products. Now, if our theory is that the choice between flavored and conventional cigarettes affects later smoking because flavored products are more palatable, less acrid, the flavor hypothesis, and therefore are more liable to hook a youth into a habit of smoking compared to conventional tobacco products, which are not as palatable, then, yeah, price needs to differentiate between these two choices. So the price would only work as an instrument for that choice if flavored products, say for a given amount of nicotine, cost either more or less than conventional cigarettes at a given amount of nicotine. So we need differentiation here. If there's no differentiation, in other words, if price does not induce any variation in the choice between flavored versus regular tobacco, then we're lacking this arrow from P to T, and hence we don't have a valid instrument. Thank you.
The next question, given that this is a longitudinal study, are the associations hazard ratios or odds ratios?
That doesn't matter. I mean, the general, the choice of, excuse me, I'll revise. So in the structure of the problem here, I said the outcome is how many cigarettes somebody smokes, say, on their 20th birthday. So that would actually be a metric outcome. We would run a linear regression on this. Now, if we change the outcome and we asked what's the effect of any smoking at age 20, we'd have an odds ratio. And if our outcome would be, if our question would be, what's the effect of choosing flavored versus nothing versus conventional tobacco at age 14 on the duration of maintaining the smoking habit, then we would likely sort of have a duration outcome and use hazard ratios.
If there are any more questions, please feel free to continue to send them in while we wait to another question has come in. It's the clearest on this topic I've ever seen. And their question is, how do we represent temporal dynamics and feedback loops into DAGs?
Beautiful question. Okay, so temporal dynamics are really easy, and they happen to be the solution to most feedback problems. So in my examples, I've just ordered the variables in time. Now, nothing keeps you from further disaggregating the process into finer time intervals. So instead of defining T as smoking versus not at age 12, we might have a temporal subscript on treatment and ask smoking or not at age 12, smoking or not at age 13, smoking or not at age 14, and so forth, right? So I have lots and lots of different T's. Now, most feedback loops, and certainly most instances of so-called simultaneity, can be resolved by articulating the effect in time. So when we're saying that, oh, you know, treatment affects the outcome, but the outcome might also then in turn affect the treatment, then usually what we mean is that treatment at time 1 affects the outcome at time 2, and outcome at time 2 affects the treatment at time 3. And so telling the story in time here, in other words, telling a causal story because causation happens in time, usually gets rid of these cycles. Now, there's some examples where you can't get rid of the cycles, so there's some theory for cyclic DAGs, but I would say that with excellent data in the biomedical and social sciences, we rarely have to worry about real simultaneity.
If there are any additional questions, please submit them. While we wait to see if any additional questions come through, just want to make a brief announcement for next week's webinar session. It's the last in this series, and the presentation is titled Estimating Causal Effects When Analyzing Data from Clinical Trials, Example of Very Low Nicotine Content Cigarettes. Registration is open, so please register, and we hope that you will join us next week, Wednesday, March 1st from 1 to 2 for the last in this series. Additionally, you will notice that poll questions will be open as well. If you could take a few moments to complete those, that would be very helpful as we continue to try to meet your needs as best we can through the sector webinar series. I don't see any additional questions coming through, so at this time I want to thank everyone for attending, thank our presenter for 2 wonderful presentations and for fielding all of the questions, and we hope that you all will join us again next week. Thank you.
Art and Alicia, are we still live? Can everybody still hear us?
Yes, we're still live. Would you like to hold on the line until we clear the line?
Yeah, so we can chat a little. Very good.